We begin our discussion of sorting with the simplest, most intuitive sorting algorithms. But before we examine the algorithms themselves, it is useful to examine the history of sorting and why it was such an important algorithm to study. The reason for its importance was a rather practical one, which is that fast sorting algorithms had great importance in the data processing era. In the early days of computing, batch processing of transactions was the norm. Such processing initially required that the transactions be sorted first. The transactions that were the input typically were on punched cards that were first loaded on disk for sorting. The reason was that computer memory was much more expensive then, and there was generally not enough to perform the sort in memory. Disk space, too, was limited, so the database was stored on magnetic tape, and the sorted transactions were merged with the database to produce one that was updated with the new transactions. Because disk accesses were relatively slow, sorting a box of cards could take a considerable amount of time even with an efficient algorithm, so having an efficient algorithm was critical. For this reason, sorting was one of the most thoroughly studied algorithms. Next, let's consider why studying sorting algorithms is important. In most cases, simple solutions also tend to be the most efficient. That is not true with sorting. Finding efficient sorting algorithms was a challenging problem. The reason is that the simple solutions are not the most efficient, and the efficient solutions are not simple. They require a more creative approach. So sorting algorithms provide a good example for studying algorithm efficiency. Moreover, many of them are data sensitive. As a result, their behavior is not always the same in the best, average, and worst cases. Although understanding the two extremes is of some importance, determining the average behavior is usually the most important. For some sorting algorithms, determining the average behavior can be complicated. Next, let's consider what arrangement of the data constitutes the best and worst cases. What constitutes a best or worst case depends upon the algorithm, which is also not what one would typically expect with most problems. Although for the simple sorting algorithms there is some consistency. The best case is already sorted data, and the worst case is data sorted in the opposite direction. There is a continuum between the two extremes, which means that the closer it is to one of the extremes, the closer its behavior would be to either the best or worst case. When we study the more complicated sorting algorithms, we will see that for one of them, the data being already sorted is actually a worst case, which may seem a bit surprising. All three of the simple sorts have a similar structure, so we will look at the code for only one of them, the selection sort. In some ways, it is the simplest because it is one of the few sorts that is not sensitive to the data when it comes to measuring its efficiency. It is the same in the best, average, and worst cases. We have placed each of the comparison sorts in a separate class that implements the generic sort interface. That interface allows an array of any type that implements comparable to be sorted. The primary required method in that interface is a method named sort that accepts an array of the generic type T. The overall structure of this method involves nested loops. The outer loop executes n times, where n is the length of the array. Recall that the selection sort is similar to the sort that would result from implementing a priority queue with an unsorted array. The inner loop is like the dequeue operation in such a queue. It searches for the highest priority element, which in this case is the smallest element. The variable min index will contain the subscript of that element once the inner loop completes. The inner loop executes fewer times as the size of the remaining elements decrease. If the element in the currently examined position is smaller, min index is modified to refer to the subscript of that element. Once the inner loop completes, it swaps the smallest element with the next position in the array. The inner loop executes an average of n over 2 times, so the method as a whole executes n squared over 2 times, which is still quadratic. Although we don't plan to look at the code for the other simple sorts, we will describe their general behavior as we describe their efficiencies. For each of these sorts, the worst case is no worse than the average, so we confine our discussion to only the average and best cases. First, the insertion sort. Recall that it is similar to the sort that uses a priority queue implemented with a sorted array. It involves nested loops like the selection sort, but the one difference is that the inner loop may never execute. The inner loop is like the enqueue operation of the sorted list priority queue. So if the value inserted is larger than any value in the array so far, the inner loop never executes. That is exactly what happens when the array is already sorted, which is why the best case is linear. In that case, the inner loop never executes. On average, however, the inner loop will execute about half the length of the unsorted portion of the array. So on average, it is still quadratic. As we already mentioned, the selection sort is not data sensitive, so it executes in quadratic time in every case. The behavior of the bubble sort is more complicated. Its behavior, in the best case, depends upon whether a check is included that will cause the inner loop not to execute if no swaps were previously necessary. Without this check, both the average and best case are quadratic. With this check, an already sorted array will execute in linear time, because the inner loop will never execute as soon as it is determined that no swaps were needed on the first pass. Structurally, all the sorts are similar. They involve nested triangular loops. By triangular, we mean that they execute in n squared over 2 times, the triangle that represents half the square. As we observed, for 2 of the sorts, the best case is better than average, the best case being when the data is already sorted. So now let's watch an animation of these sorts to get a better idea of how they behave. And we'll begin with the selection sort, which is the one that we looked at the code for. So notice what's happening here is it's going through all of the blue elements, and it's looking for the one which is the smallest. And then it's taking and it is swapping that with the next element in the array. So the ones that appear on the left in red are already sorted, and the ones that are in blue on the right are the ones that are being searched. So that gives you a general idea of how that one works. Okay, so next let's make a new array and do the insertion sort. So the way that the insertion sort is that it takes each element and it inserts it into its proper position. So it's each time it's taking the blue bar that is furthest to the left, and it's performing an insertion among the red bars. And so all the red bars are sorted, and the blue bars are those still waiting to be sorted. All right, and then finally, let's take a look at the bubble sort. And of all of the sorts, the bubble sort is the least efficient, and you'll see why watching an animation of this. The way that the bubble sort works is it compares adjacent elements, and it swaps them if they aren't already fulfilling the condition that the one on the left is smaller than the one on the right. So it goes through from the right side to the left side, and this process is the process referred to as bubbling through the array. And after it goes through this lengthy process, one pass through, what we'll see will happen at the very end is that once it completes one pass through here, the only thing that will have been accomplished is one element. The element in red on the left is in its proper position in the array. So this one takes considerably longer. So we won't watch the remainder of this, but you get a general idea of how that one works.